Does anybody have homework questions?
I did it last night, and I started my exams.
I don't even know if I did.
You did. You told me you did. And you told me you did really good. And then you did review one question. You fixed it.
Remember, we were looking in 3.3 to see if there is an infinite set bigger than the natural numbers. And Cantor had said that there was, and we were studying his theories, his ideas, that there are sets larger than the natural numbers in size. So we're going to be considering the counterintuitive. If you just think infinity is infinity, then the idea of different sizes of infinities is counterintuitive. So let's just review where we were at. Thank you. So we had been looking at dodgeball as a way to look at different size sets. So if you remember, we had come up with a way so that player 2 could win at this dodgeball game. Player 1, if you recall, wants a match. Player 2 is trying to dodge a match. So that's why it's called dodgeball. Player 2 is trying to avoid a match. So we had come up with a way for player 2 to always win. And that was to just look at the diagonal and be different on the diagonal. So for the first row, there's an X in player 1's column, and so player 2 puts an O, and now player 2 will be different from the first row for sure. And then player 1 starts trying to copy player 2, but player 2 is on the ball, so player 2 just watches that diagonal and is always the opposite of whatever that diagonal is. And that way, player 2 won't match row 2 either. So player 2 just continues on in this way, watching player 1's diagonal, and always is different for player 1's rows because player 2 is different from one box for sure on each of player 1's rows. So in the fourth row, player 2 is going to be different in the fourth box. In the fifth row, player 2 is going to be different in the fifth box. And in the sixth row, player 2 will be different in the sixth box. So player 2 is always different by at least one box by watching that diagonal. So that was our strategy that we had. So player 2 can always win in a standard dodgeball game. By watching the diagonal. So player 2 can always win by watching the diagonal in a standard dodgeball game. But we had found a way for player 1 to win. Okay? Player 1 can win if player 1 is allowed to list all possible combinations, XOXO combinations So if player 1 lists all the possible XOXO or XXOO combinations, then that's not that hard to do. I mean, it takes some time, but there's only 6 columns, and so there's only extra O, extra O, or extra O in each of those boxes. That only makes 2 to the 6 possible combinations, or 64 different possible listings. So player 1 could win in that case. They just list all the possible ones, and then player 2 is like, well, you listed everything possible. There's no way to dodge that. So now I'm going to make it harder for you. Okay, here's what we're going to do. Player 1 can make as many different exo combos as they want. In fact, player 1 is going to make infinite combinations because we're going to extend the board. We were just looking at a board 6 rows by 6 columns, or we switched to 64 possible rows, but still 6 columns. Now we're going to take this board and we're going to make the board have an infinite number of rows and an infinite number of columns. Okay? So we're going to have player 1 able to make as many different combinations as they want, list as many rows as they want. In fact, they can list an infinite number. But there's going to be infinite rows, so I'm going to go dot, dot, dot here. Okay, so remember that means that goes on forever. And dot, dot, dot. So the rows go on forever too. So infinitely long rows going on forever. So player 2 is going to take and look at the player 1's list. And then player 2 is going to make their row. And their row can be infinitely long, so we'll put a little dot, dot, dot at the end. But my question for you is, now who's going to win? So the board's infinitely wide, infinitely tall. Player 1 lists as many rows as they want to. Can player 2, after player 1 say list all the rows they want to, can player 2 come in, or even if they take turns going back and forth, can player 2 come in and win? Or is player 1 going to win now? Who wins? Who wins? Does anybody have any ideas? Yes.
Player 2?
Player 2. And why would player 2 still win?
Because if there's an infinite amount of numbers, it's like really hard to get a match.
Oh, but they have an infinite long.
Oh.
Yeah. So they can go infinitely long. So since they can still do an infinite number of rows, that there's an infinite number is going to make it harder, but it's still not the reason why. Does everybody see why player 2 can still win? Yes.
Because with the infinite, you can still go like with the diagonal.
Yes, so they can still go on the diagonal. So player 2 can still keep this strategy up because these are listed. These are all listed. So player 2 can go down the list and make the 7th box different from the 7th row, 7th box, and still be different then. Player 2 can go to the 1000th box for the 1000th row and be different from the 1000th row. So player 2's list of X's and O's is a row that's as wide as they want, and so when they come to whatever row they want to be different from, they just make that corresponding diagonal box different, and they'll always be different by 1 box. Okay, so who wins? Player 2. Just watching that list of X's and O's. So what you've done then is you've said that even if we have an infinite number of rows here that are infinitely long, there's always one that's not on that list. As long as these rows can be counted off in a list like this, there's always one that's not on the list. Even though there's an infinite number of rows on this list, this is one row that's not on that list. So you've found then an infinity larger than the infinite size of the natural numbers. So this this chart that goes on forever is an ordered list. It has a one-to-one correspondence with the natural numbers. And here you found one that's not included in that one-to-one correspondence and cannot be included. So you found an infinity larger than the infinity of the natural numbers. So always go back to our basics. Two sets are exactly the same size if and only if the elements from one set can be put in a one-to-one correspondence with the elements of the other set. And we have just found a set that cannot be put into a one-to-one correspondence with the natural numbers, the set of all possible rows of XOs, XOs, XOs. Because if we try to put them in a one-to-one correspondence with the natural numbers and say, here's that correspondence, we found one that's not on there. Well, let's see, how does this relate to numbers, okay? Let's go, how does this tie in with numbers? Recall that all real numbers can be written with an infinite decimal expansion. All real numbers can be written with an infinite decimal expansion. So now you don't have to write all real numbers like that. Some numbers, decimal expansion just terminates, like 5.2, okay? 5 and 2/10, or 52/10, which is in fact the same as 26/5. But if you wanted to, you could write it with an infinite decimal expansion just by tacking a bunch of zeros on the end forever. So all real numbers can be written with an infinite decimal expansion. So let's take a look at how these decimal expansions differ. So let's take a look at the number A. The number A is bigger than 0, so it starts with 0 point something. It's bigger than 0 and smaller than 1. And I'm not telling you the first 3 digits of the decimal expansion, but the 4th digit is a 7. And I'm not telling you the rest of the decimal expansion. In fact, I'm Xing it out. So those X's are hiding the digits that make up the number A. So here's the number A's decimal expansion, and all you know is that it falls between 0 and 1, and the 4th decimal place is a 7. What I'd like you to do is to write a number.
That's frozen.
Thank you. Write a number between 0 and 1. Write a number between 0 and 1 that you are positive. That you are positive is not the number A. Okay, so you can only see one digit in A's decimal expansion. But even so, I'd like you to find a number between 0 and 1 that you are positive is not the number A. So your number falls between 0 and 1, so it starts with a 0 point something. Does anybody want to tell what number they wrote down that they are positive is not the number A? Yes.
0.0006000.
Good. So 0.0006000 dot dot dot. And how did you know this is not the number that is A?
Because where the 7 would be is not the same number, so there's no way that it can be the same number.
Good. Because where the 7 is in the 4th decimal place of A is a 6. So as long as this number that you made has a 4th decimal place that's not a 7, then you did this correctly. Okay? because that all you have to differ from one number to another is one digit, and then you're a different number. Let's try that again. This time we'll look at the number b. So for b, it's also a number between 0 and 1, so it starts 0 point something. And I'll X out the first two decimal places, and then there's a 2, and then I'll X out the rest. So we only know the third decimal place is a 2. So once again, can you find a number between 0 and 1 that you are positive is not the number b? So I'm going to write one also. I'm going to pick 0.1, 2, 3, 4, 5, 6, 0, dot, dot, dot. Okay. So your number is correct as long as in the third decimal place you do not have a 2. All right? So numbers have all numbers, all the numbers that we use that don't have an I, so all the real numbers, the rationals and the irrationals, have a decimal expansion that's infinite. And as long as you're different from one decimal place, in one decimal place, then you'll have a different number. So we're going to use that as we look at finding a infinity that's larger than the infinite size of the natural numbers. For a set to be the same size, or we call that cardinality with sets. For a set to be the same size or cardinality as n, the natural numbers, means that its elements can be listed. For a set to be the same size or have the same cardinality as n, it means that its elements can be listed. That's why when we were making one-to-one correspondences between sets, we would make we'd list out the elements of n, and then we'd list out the elements of the other set. For example, the integers, remember the integers, those were the positive and negative whole numbers, and 0. So we started out with 0, then we went to 1, then we went to -1, then to 2, then to -2. So we just had to find a way to list those integers, and then they could be put into a one-to-one correspondence with the natural numbers. Well, we're looking to show that a set cannot be listed. That will make a set that's larger than the set of natural numbers. Okay, to show, let's write that down. To show a set is larger or has a greater cardinality, is larger than the natural numbers. To show a set is larger than the natural numbers boils down to showing that the elements of the set cannot be listed. To show a set is larger than the natural numbers boils down to showing that the elements of the set cannot be listed. Now, that doesn't mean cannot be listed right away. Remember how when I first gave you this set of the integers and you were trying to come up with a one-to-one correspondence, it took some time? We have to have, not that it's going to take several tries to get the one-to-one listing, but that it's completely impossible to get the one-to-one listing. And this is what Cantor realized. He boiled it down to this essential fact, and then he was able to show that it is impossible to list all the real numbers in a one-to-one correspondence with the natural numbers. To show that it's impossible, he's thought about, well, what would a list of real numbers look like? What would a list of the real numbers in one-to-one correspondence with the natural numbers look like? Okay, so the real numbers are all the numbers that you know. The natural numbers are these nice counting numbers that we use. If there was a way to make that, what would it look like? What would it have to look like? And how can we make sure that how can we see that it's impossible? So you don't have to write this down, but I have a couple samples of what it would look like, and there's another sample in the textbook. So it looks something like this, right? You list your natural numbers, you list your real numbers. They're in one-to-one correspondence. 1 goes with some number, 2 goes with another, 3 goes with another, and so on. Let me grab a piece of paper. Actually, I'll pull this piece of paper and work it upside down. Okay, so if there is such a list as this, Cantor said this cannot be an exhaustive list. So it's like dodgeball, when someone does all the infinite rows they want to and then hands it to player 2 and says, look, I've listed all the rows, you can't win. And player 2 says, yes, I can. I have this great diagonal set strategy. Cantor has a wonderful diagonalization strategy. So what Cantor does is he says, suppose there is such a list. I'm going to find the missing number we'll call M. And by the way, this is a type of quiz question that I'll give you. Okay, I'll be giving you these lists of numbers like this and say, use Cantor's diagonalization proof to show that it's impossible for the natural numbers to be in a one-to-one correspondence with the real numbers. And then I'll give you this list and you'll have to use his proof. So what Cantor did is he said, okay, here's this number between 0 and 1 that I am positive is not on the list because we're going to be different from the first row in the first decimal place. We'll be different from the second row in the second decimal place. We'll be different from the third row in the third decimal place. Will be different in the fourth row in the fourth decimal place, and so on. So here's what he did. He said that our default number will be 8. But if that decimal place we're looking at is an 8, and we want to be different, right? So if that decimal place is an 8, we'll use 5. So you could use any two numbers, but these are the two that we'll use here. So I look at the first row, and I say, well, there's a 3 in the first decimal place, so I'm going to use my default digit of 8. Now I won't match the first row. I won't match the first real number. The second real number has a second decimal place of 4. So I'll again use my default digit of 8, and now I know this number I'm named M will not match the second row. In the third row, I look at the third decimal place, and it's an 8. So I don't want to match And so since it is an 8, I'm not going to use my regular old 8. I'm going to switch to the 5 now. So my 5's the alternate. So we use the 5 because now we'll be different. From the third row, will be different in the third decimal place. So we're looking always at the diagonal. In the fourth row, we want to be different from the fourth decimal place. So 1, 2, 3, 4. Fourth decimal place is a 0. So I go back to my 8 again. Fifth decimal place for the fifth row needs to be different. So 1, 2, 3, 4, 5. The fifth decimal place is a 4. So I'm going to use my default 8. And then I'll be sure that I don't match the fourth row's number because I'm using an 8 there. And there was not an 8. So I differ in the fourth decimal place. I differ in the fifth decimal place. How about the sixth decimal place? 1, 2, 3, 4, 5, 6. Oh, there's an 8 there. Okay, so the sixth decimal place, am I on the right line? Yes, the sixth decimal place is an 8. So I'm not going to use my 8 because I want to be different. So I'm going to use the 5. So I default to the 8 unless it is an 8 because I want to be different. Then I use the 5. So it's kind of like X's and O's, but we're just sticking with 8s and 5s. Let's see. Now I'm on 7. 1, 2, 3, 4, 5, 6, 7. So the seventh decimal place is an 8. And so to be different from the seventh row, I won't use the 8. I'll use my alternate choice, my 5. Okay, then I'm going to put a dot, dot, dot to show I'm continuing the pattern. And I'll go to the 11th row. And there I want to be different from which decimal place? 11th. Perfect. So let's look at the 11th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Did I count right? Yeah. So the 11th decimal place is a 2. So I don't want to be a 2. So I'm going to use my default of an 8. And then I'll go dot, dot, dot to show this pattern continues. So Cantor said, suppose there is a one-to-one correspondence between the real numbers and the natural numbers. Write it down. And I will show you a number not on that list. So if anybody hands a list saying they have a one-to-one correspondence between the real numbers and the natural numbers, Cantor found a way to find a number that's missing from that list because it differs from the first spot in the first decimal place, second spot in the second decimal place, third row in the third decimal place, fourth row in the fourth decimal place, and so on. Now, as I said, this is a quiz question. I do put on quizzes, so I'd like you to have a try at this. So I have another list that's similar. Either that one or this one you'll need to do as a class activity. So you can go ahead and put your name on here, okay, and take a picture. You don't have you don't have this showing, so just your missing number that you're sure is not on the list, okay. After you get that uploaded, then you can do this next one. Let me decide if we're doing 8s there as well. Yeah, that'll be fine. Okay, so you can use 8s and 5s there as well, and have a try at this second list. So default is 8, else use 5. And create the missing number m. Don't forget, let's put that in red because then when you're studying your notes, don't forget the 0 point something, okay? And I have to slide this down. And you can work on this, and we'll Nicholas and I will get ours figured out too, and then we'll come around and see if you're getting the hang of finding this missing number that can't possibly be on the list. I mean, I know it's a finite list, and you can say, well, the number 5's not on there, I'll just write 5. But remember, we need a pattern that goes on forever, because your 5's probably down on the list otherwise somewhere. If you think you have it, raise your hand, or if you're stuck, raise your hand and we'll come around and check. First I'm going to compare it, Nicholas. Make sure we both see our, not seeing double.
Yay, we did it. Not his father. I'm gonna see if he's gonna be home when I get back, so I can talk to him.
Okay, so how was your school?
Oh, it is me, sorry.
That looks good. I think you maybe put X-ray.
Oh,
Yeah. Yeah, you have an X-ray too? Let's see, how many do we do? 1, 2, 3, 4, 5, 6. I bet I'm missing one.
I think you are.
I am missing 8.
I think you're missing the 7th.
yeah.
Thank you. Must be the 6th row.
Yeah.
Early 2000s.
Okay, thank you. Good job. There we go.
In Halo, so they would put the heads up and down.
Let's see, there's one more.
This one?
Third one.
It gets pretty deep into later seasons, so you're like, wow, how did they show me for the first line? Why are we here?
Yep.
See if he's gonna be there. I don't know where else he's gonna be. I doubt he's going to Milwaukee this weekend because he has to go to my stepmother's birthday party. Because he goes there to Milwaukee, it's $70 for a round ticket for the bus. I know. I'm like, dude, why? That's because he got trapped once in
You're gonna make me
Milwaukee.
cry to go.
So it's 8, right?
I think he'll be good. Okay, go. You don't have anything here. Yeah, it doesn't really matter. Just go be.
Yeah, that's why I messed up my comment. I come to 7. I'm tired.
So it doesn't matter.
Yes, I'm on for tomorrow morning. And just give me a 10, I'll get up at 9.
That's when you use a 5.
Oh.
Whatever kind of matters.
And then,
So early service. Oh yeah. So did these work out for you? Yeah, there's 3.
Nah, bro. I'm a nah, bro now. Oh my.
Okay, so look at that third.
I mean, spend night there.
And the third, that's what.
She falls asleep early at her. Like,
So that's what you're about.
what am I gonna do?
Yeah.
Just lay there. So. I have a meeting at 1. And then we get lunch at 12:30. And it takes 10 minutes to 1. So we got like 10 minutes. I got like 20 minutes. I'm gonna walk to the cafeteria. Why? No, the cafeteria is like buffet booth.
Committed myself.
Yeah, I did it, and then my friend group does now, so I just go there and meet with them.
Okay. I don't know if I should be considered. I'm gonna text me back. Okay, he's never called. He's never like, are you my mom? He's like, nah, bro. I'm like, I'm out here. What? Look at this. What is that?
No, bro, I'm out yet.
What am I? I'm not his bro. I'm his sister. There's a difference. We don't talk like that. I'm questioning his life choices right now. Wait, I've been questioning his life choices his entire life. Yes. He hasn't got arrested yet, so we're good. If he gets arrested, I have to bail him out, by the way. I gave him one get out of jail free card, meaning I bailed him out of jail. He's got one of those.
Yeah.
If he uses it, I don't know what to do. It means he screwed up his life somewhere. Because I have not ever gotten trouble, not even with school. My brother's got, he has gotten in much detention. I have never gotten in much detention.
So when I say default 8, we mean always use 8. Unless it is an 8. Always use 8 unless it is an 8, and that's when we go back to using a 5, because that way we won't match. So we're never going to use the 8 when there is an 8 there. And if there is an 8 there, we'll be using a 5. So we have decimal place 1 is a 2, so we put an 8. Decimal place 2 is a 4, so we put an 8. Decimal place 3 is an 8, so I better use a 5 now, I won't match. Decimal place 4 is a 7, so I use my 8. So I'm always using an 8 unless it is an 8. And then I use 5. So in this way, we found a number that cannot possibly be on the list because we're always different from the row by 1 decimal place. So for example, this goes out 100 decimal places, and in the 100th decimal place, I'm not going to match the 100th row, because if there was an 8 in the 100th decimal place, well then I'm putting a 5. But if there wasn't an 8, then I am putting an 8. So I'm not going to match. Let's put this out as actual proof. This is a good quiz question though, so make sure you know how to do this. And you'll see extra practice of this on the Mindscapes. I listed a few extra practice ones by the review on Canvas, so that when it comes time to take the quiz, you can go back and practice. But if you were a little iffy on this, you should probably go back and practice now. So the ones on the Mindscapes, use the read, study, practice area in Wiley, and the chart on Wiley, and the Mindscapes at the end of that section 3.3 to practice some more. They're okay. Okay, so let's write the actual proof that Cantor gives to prove that the set of real numbers has a larger infinity than the set of the natural numbers. So this is Cantor's diagonalization proof Cantor's diagonalization proof that the real numbers, you can abbreviate with the R with a double bar, capital R with a double bar. The real numbers have a larger cardinality. We can think of that as size. A larger cardinality than the natural numbers. So the natural numbers are infinite, but all infinities are not the same. We have a larger infinity now, the real numbers. So here's how the proof goes. Suppose that there is a one-to-one correspondence. Suppose that there is a one-to-one correspondence between the natural numbers and the real numbers. Suppose that there is a one-to-one correspondence between the natural numbers and the real numbers. This is fixed. Okay, that's it. It's done. You're like, here's the one-to-one correspondence. There was such a thing. Here it is. Let me hand it to you. Okay. Then let m for missing number, let m equal 0. And now I'm going to put d sub 1 for the first decimal place. So the little subscript 1 means the first decimal place. D sub 2 for the second decimal place. D sub 3, D sub 4, ... Okay, so we're going to let m equal this new number, this number that we're creating, and now we're going to describe how it's created. And it's just like what we did, only Cantor's original proof used 2s and 4s, so that's what we'll use. Let d sub 1, the first decimal place, let d sub 1 be 2, if the real number corresponding to the natural number 1 if the real number corresponding to the natural number 1 has a first decimal place that is not 2. Let d sub 1 be 2 if the real number corresponding to the natural number 1 has a first decimal place that is not 2. Otherwise, d sub 1 equals 4. Otherwise, d sub 1 equals 4. So here the default number that we're going to use all the time is 2. But if that decimal place is a 2, then we're going to switch over to 4. Okay, then we'll do the same thing, but now we'll look at the second decimal place to go with the second row, the second natural number. So let d sub 2 be 2. So we're writing almost the exact same thing now, but now with the second row and second decimal place. Let d sub 2 be 2 if the real number corresponding to the natural number if the real number corresponding to the natural number 2 has a second decimal place, that is not 2. So d sub 2 be 2 if the real number corresponding to the natural number 2 has a second decimal place that is not 2. Otherwise, d sub 2 equals 4. Now we could keep doing this forever, right? Because there's an infinite decimal expansion, but we're just going to say continue in this fashion. Okay, so we're creating this number m, created in this fashion. Going to put in 2's whenever the decimal place is not a 2, but if the decimal place is a 2, then we'll use a 4. Okay, so m is not on the list of r. So m is not on the list of real numbers because it always differs from each row by at least 1 decimal place. So m is not on the list of real numbers. So there is no one-to-one correspondence There is no one-to-one correspondence between the natural numbers and the real numbers. There is no one-to-one correspondence between the natural numbers and the real numbers. The cardinality of the real numbers is larger than the cardinality of the natural numbers. The cardinality of the real numbers is larger than the cardinality of the natural numbers. Remember, that means the size. So we have a size of an infinity that is larger than the size of another infinite set. Okay, they have the natural numbers here, and we have the real numbers here. The real numbers are a larger set than the natural numbers. And we've proven it. Cantor proved it. So this was quite earth-shattering at the time, and even now it can lead to some interesting discussions and arguments. I don't think I've still convinced my husband of this, but on the other hand, he did not want to sit and look at the proof. So there immediately comes to mind, hopefully, is there an infinity bigger than the real numbers? I mean, does this just keep going? I don't know. Well, I do. Soon you'll know too. We're going to look at 3.4 and look at 4 questions on 3.4 that we want to have answered by the end of that section. So they're fairly early on in the section here. If you have a textbook, it'd be on the first page, but you'll see them listed out on the website as well. So today what I'd like you to do is take a piece of paper as we're going through these questions and just decide which question is hardest to answer. Which question is hardest to answer? Oh, you know what? I wrote it in a Post-it note, so I'm just covering up the question with the question. All right. So there's 4 questions. You can go ahead and fill in the box at the end. Okay, first question. Is there an infinity that is greater than the infinity of the set of natural numbers, yet less than the larger infinity of the set of real numbers? Okay, we had the natural numbers have a smaller cardinality than the real numbers. Is there something in between there? Okay, is there something in between? Okay, so that's what we're asking. There's some size of infinity that comes between the size of the infinity of natural numbers and the size of infinity of the real numbers. Question 2. So this was number 1. Question 2. Is there an infinity greater than the infinity of the set of real numbers? So is there something larger? Okay, is there something larger than the real numbers in size? Question 3. Are there infinitely many different sizes of infinity? So question 2 is there one bigger? Now question 3 is, are there infinitely many? So there'd be infinitely many sets that are larger than the set of real numbers. And number 4, is there a largest infinity? One that encompasses all others. So we have 2 sizes of infinity, which you maybe didn't suspect at the beginning of the semester. And now we're wondering, well, where does that lead us? So we're going to look more at infinity next Monday. I'll see you then. Have a wonderful weekend.
I like having a drawing.